Now, to understand how water is released from storage in the vadose zone, let's do a thought experiment. So if we have a disk here of soil, and we use a porous ceramic plate here at the bottom, so we can pull suction on this disk, and we can pull suction on the water to pull it out, but we don't let air enter in through this disk. Then we take this tube, and this is just a flexible tube, and we fill it up with water, and initially it's filled with water up to there. Okay, and so everything's in equilibrium, the soil is saturated, and then what we do is to move the soil, or move the tube down. And so we can physically actually just move the tube until we get down to the water level down to there. And now what we've done is put this much suction on the soil. And that's going to cause water to be pulled out of the soil, and we'll have then some water come out of the soil and come into the tube and fill up the tube up to that point. And then we can take the tube and move it again and move it back down to this point, and then write down how much it rose, and that's the amount of water that came out. And then we do it again, and you might imagine that it would rise up a bit less the next time, and so we repeat that, and we keep track of how much it rises up each time, and eventually we find that it just is stable at that point. So what's happened is we've put this much suction head on the soil, and we've pulled out a certain amount of water that we keep track of, and we add it up, and that's the amount of water that has been pulled out of the soil here by the amount of suction that we've applied. And so as we do that, what we might imagine is that the water, which is held in the soil by capillary forces, it's going to be more tightly bound into the small pores than in the large ones. So when we do this, and if we first get some water rising up here, the water that comes out initially will probably be the water that's in the large pores. Those are going to drain out first. And then we'll have water going from the large pores. We're going to have water, we're going to have the pore size progressively decrease that we're draining water from. Okay? So that's just basically a conceptual idea. And actually, though, this is a test that's done to determine how the change in water content is affected by suction at relatively small amounts of suction. So this kind of test here is done in the laboratory. And what we might imagine then is if we do this for one suction head, then we change the amount of water content that's in this soil. And so if we plot this up, this is the water content here. And so right here at 0 suction, this would be the saturated water content. That's where we start. And then if we put this much suction on it, and that corresponds to, say, this much suction head on this axis, this is going to be suction here on the x-axis. And then we reduce the water content of the soil by this much. So we started here and we reduce it by that much. That's the water that accumulates as it rises up in the tube. Then the water content would now be at that point. And if we repeat this and drop this tube down lower, we would get another point here and another point here. And what you might imagine is we're pulling water out of progressively smaller and smaller pores. And at some point, the water that's going to be able to flow out is going basically over some smaller and smaller channel ways. and it's flowing out over some thin films that go along the surfaces of grains. And eventually what will happen is that the water that exists in the soil is only occurring in small pores, and those little pockets of small pores are isolated from other small pores, and there's not really any way for that water to flow out. So we could pull harder, we could put more suction, but there's no way for the water to flow out, and so we stopped getting additional water to come out. And so as we put more and more suction, what we see is that the water content really stops dropping out, and dropping down, and we go and approach what we'll call a residual saturation. So this curve here is determined in the laboratory, and it's called the soil moisture characteristic curve. I'll get to that in just a second, but let me point out that what we might imagine too is, as we do this experiment, if I were to take this point in the tube where the water level is, I start out with it up here in equilibrium, and we might imagine that I could drop it down to here, and there would be no change. That with some small amount of suction, the soil can simply hold on to the water and prevent it from leaving, and actually what's happening is it's preventing air from entering the pore structure. And so if that's the case, I can put some suction on the sample, and there's no air entering, and so the water content stays the same. So this curve is flat for a little bit, and then I reach a certain amount of suction here when it starts to decrease. Well, that's a particular suction right there. That amount of suction is what's required to have air enter the pores, and so that's called the air entry pressure. And for fine grain materials, for the fine grain ceramic that's used in tensiometer tips, this can be quite a high pressure. For soils, it's for sand, it can be quite a low pressure. But nevertheless, this will be an important point on this curve. This is the air entry pressure. Air entry, or I guess if we're plotting suction, the air entry suction. So there I'm calling it the air entry pressure. And then this here, this water content, is the residual water content. So as it decreases, it approaches that residual water content. Okay, so that's how the water content is responding to changes in the pressure head or the suction. This is called the soil moisture characteristic curve, or the capillary pressure curve. One way that this is manifested out in the field is that if we look at this cross section, we've got a water table here, and by definition the pressure head there is equal to 0. Well, since we know that there's water up here in the vadose zone, and this water is being pulled up by capillary pressure, there's going to be a zone up here. There's going to be a zone like that where the pores are saturated. They're filled with water completely, but the suction head is, well, the pressure head is less than 0 because it's above the water table, but the pores are completely filled with water. So this is called the capillary fringe. And the height of the capillary fringe above the water table is going to be equal to the air entry pressure head. Okay, so for fine grain sediments, fine grain materials, this may be several meters. For sands, it will be much smaller than that, perhaps a centimeter or so. Okay, in that case it's probably negligible, but it certainly is possible for the capillary fringe to occupy an appreciable zone where the soil's under suction, it's above the water table, but essentially the soil is saturated. Okay, so we have this soil moisture characteristic curve, and what I've done here is plotted the curve for several different types of material. this is a well-sorted sand, and if we go through our thought experiment of applying some suction and pulling the water out of the soil, what we might imagine happens for a well-sorted sand where the grain size is very similar and the pore size would be similar, is that you apply some suction and maybe not much happens, but then you get enough suction applied to the soil to drain the pores. And since all the pores are about the same size, and since the pores drain in inversely, since the amount of suction that's required to drain the pores is inversely proportional to their size, you reach a certain size and then they all drain, and you drop off the moisture content over quite a narrow band of suction, and then you reach this residual saturation. So this is what a moisture characteristic curve might look like for a sand. For a sandy, silty clay, you might expect then there would be a fairly wide range of grain sizes, some large pores, and well, you might expect you would know that there was a wide range of grain sizes because it's a sandy, silty clay. So the grains range from sand down to clay, and you might expect then that there would be a fairly wide range of pore sizes, some fairly large pores and some small pores. And as a result of that, the moisture characteristic curve, when you start to put a suction on this, you might have some large pores draining here with some small suctions, so a small change in the moisture content. And then as we get progressively higher and higher suctions, we get we're reducing the water content progressively, and that keeps happening out to very high suctions. Okay, so for sandy, silty clay, we might expect the soil moisture characteristic curve to look like that, and this would be something in between, or a moisture or a soil in between. Okay, so the soil moisture characteristic curve, this will be an important curve for describing how soils will release or take up water from, put water into storage or take it back out. This is the plot that we saw previously. There are a variety of ways that this is displayed. Here's the same plot, just with the axes switched, shown here. And you might see it instead of like this, which is how I plotted it. If we plot it using pressure head is becoming more negative in that direction and more positive in that direction, then the moisture content would look like this, where we use pressure head as an axis. All right, and so now we're going to be interested in how water is released from storage due to a change in the head. So recall that the water content that we're using, it's the volumetric moisture content. That's what I've been using here on the y-axis for the plots that I've been showing. And that's going to be the volume of water in the soil per total volume of soil. Okay? Well, if we take this and we take the rate at which the volumetric water content changes due to a change in head, so the derivative of the water content or the moisture content with head, then what that's going to be is how the moisture content changes when the head changes conceptually. Okay? Well, if we write this out as, if we write this like this, let's just cover that over. That's the water content, the volume of water stored per total volume. And so I put that delta in there. That means change. So we have this means the change of the volume stored per total volume per change in head. Okay? So this is going to be equivalent to that. All right, well, the significance of that is, if you recall, the change in volume stored, or the volume released from storage per total volume per change in head. That's what we've called the specific storage. So when we were in the saturated zone, this was something that would happen as a result of compressibility of the fluid and compressibility of the aquifer. But in the vadose zone, we have a different process. We can drain the pores, and if we go to this soil moisture characteristic curve, where we're plotting the volumetric water content as a function of the pressure head, then remember the total head is equal to the pressure head plus the elevation head. So if we do this on a sample that's at a fixed elevation head, then the change in water content per total head will be equal to the change in water content per pressure head. Okay, so this thing that we've written here will be essentially the slope of this plot. Okay, so this slope here is going to be this thing. And so what that tells us is that the specific storage, conceptually, the idea that we had for the specific storage in the saturated zone is equal to the slope of this curve here in the unsaturated zone. Okay, so that allows us to make a connection for how we might have this concept that we developed in the saturated zone and have it apply here to the vadose zone. Okay, so that'll be an important step. Yeah, actually, let me erase this and point out this terminology. So we called it the specific storage in the saturated zone. In the vadose zone, this is typically called the specific water capacity. And conceptually, though, we can think of it as the same kind of thing as the specific storage. How much water we're going to put into or take out of storage if we change the head, at least on a per volume basis. Okay, so the soil moisture characteristic curve is going to be an important thing, and there are a couple of ways that this is characterized. The Van Genuchten curve is perhaps the most widely known. This says the water content is equal to, there's the residual water content, there's the saturated water content, so we've seen what those are. And then we have two terms there, this term alpha and this term N. And those are fitting terms. And the way that those are determined is to do an experiment and come up with what the volumetric water content is as a function of the pressure head. And the experiment, like what we saw a few slides ago, where we had a soil and we put a suction on it and we pulled water out progressively using that tube, that gives us these data points. And then this curve here, this function, gives us a curve that we will plot here and adjust this term alpha and N in order to fit these data. So we end up with something that looks like that. That'll give us a value of alpha and N that does that best fit. This is another one, Brooks and Corey, and it's giving us the water content also as a function of the head. And this would be, here's the residual, here's the saturated, and that's HB, that's the air entry pressure, and there's a fitting parameter. And in this case, I should point out that what I'm calling H here, that should be the pressure head. Okay. So to make it consistent with this plot there, and it needs to be, need to think of it in terms of the pressure head. Okay, so those will be important functions that we'll use to characterize how soils behave in the vadose zone. So there's the fit that we would do. And we can use various different methods of curve fitting to obtain these parameters. Some of you will have done an exercise where you used solver, for example, in Excel to fit the Van Genuchten equation to data.